How's everybody doing?
Good.
Good. How's the midterm going?
Good. Not bad. Not too bad. I do have them.
It shouldn't be, if you run into problems or questions you have, just email me. But everything that is on there is in the notes somewhere. Okay, so it's all there. I wouldn't ask you to do anything that I haven't taught you or haven't discussed. Okay, but still, anyways, if you need something cleared up, don't hesitate. Okay, that's the whole point of a take-home exam, is to get it right, even if we have to discuss the answers. Okay. So last time we finished up our calculation of the 2-point function, right? So this is the loop that we were trying to compute. Why isn't it? I need to be over here. Isn't it moving? Okay, now it's moving. Now it's moving too fast. Okay. All right, so we were computing that 2-point function, and we saw that there are a lot of little tricks here and there that you can use to evaluate these guys. So one is the Feynman trick, where you introduce a new parameter to combine those denominators, and you have to it replaces a tough denominator with a simpler denominator, but you end up having to integrate over these parameters, which is not a problem because most of the time it's really easy to implement numerically. Okay, and so we'll see how it's extended to integrals with more than two denominators. So this was the guy that we wanted, right? And so we started out by just introducing one Feynman parameter, right? So that means we multiply one denominator by x, the other one by 1 minus x. You combine everything. The next step is you want to complete the square, because you want something that's spherically symmetric. Okay, because we noticed that if we could get it into a spherically symmetric form, then hopefully there's a chance that we could do at least some of these integrations analytically. All right, so that's what we did. So we combined completed the square, and you get down to something that looks like equation 38, which is q squared plus some constant stuff. Right? Q squared is the guy that you want to integrate over. It's the new momentum that you introduced when you completed the square. How can I get this guy off here? Okay. Damn it. Technology. Okay. Yeah. Right? And so this was where we were, right? And we wanted to evaluate this. We noted that it's spherically symmetric, but we're in Minkowski space, right? Where the metric doesn't have a plus type of signature. But we could do what we call a Wick rotation, right? Where we rotate the integration of the Q0, the Q0, and rotate it off of the real axis onto the imaginary axis. And the reason we can do that is because they're poles, right? And we know from the residue theorem that the only contribution is going to come from the poles. So as long as we don't cross any poles in this rotation, we're allowed to do this. It's a mathematical trick that physicists stole. Okay. And so what it does, it allows us to get something that's more Euclidean, right? And if it's Euclidean, then it looks like something spherically symmetric. And so we can do this integral. It took us a while, but we could do it. So this is stuff I skipped over. But to do the integration, we need to, use another trick, which was dimensional regularization, or DIMREG. And so that involves moving away from d equals 4 or d equals 6 dimensions, whatever dimensions you're working in, moving below those dimensions where these integrals are finite. Okay, so you compute them in the finite limit, and then you take the limit where d goes to whatever dimensions you're working in, and the infinities will show up as poles in one of the parameters that you introduce. Okay, so that was our idea, or that's the idea behind DIMREG. And so we went through some tricks to compute the spherical, angular part of the integral, right? And we showed that. And gamma functions pop up everywhere. Whenever you're doing loop calculations, you'll have gamma functions all over the place. So it's best to know how to handle them and all the little tricks and identities that come along with them. And so what we do here, so we got to a point where we could do the radial part of the integration. Right? To do that, I made another change of variable. I replaced q bar squared, which is just our rotated q, by z, right? And that allowed me to get down to something that looked like this. And this I can do because it's just what we call a beta function. Okay? And so that was, there we go there, right? Now I wrote down the beta function. Again, it's in terms of, gamma functions. And so you plug that in and you get to some answer in some arbitrary d dimensions, okay? Now still remember, you still have to do this integration over x, but like I said, you can do that at the end of the day just using numerical techniques. Okay. All right, so before we moved on, we said, well, wait a minute, we want, we started out with a coupling that was mass dimensionless, didn't have any mass dimensions, right? And we wanted to keep it that way because theories that have zero mass dimension couplings are renormalizable, okay? If they have dimensions, we'll see that all hell breaks loose, okay? So what we did was we rescaled our coupling when we moved into these arbitrary d dimensions. We moved in, we shifted our coupling and shifted the mass dimension into some unknown parameter, okay? It's some unphysical scale, doesn't correspond to anything physical, but we just move it off into that mu, okay? What can I get coffee out? Oh, long day, okay? So we did the calculation and we replaced d with 6 minus 2 epsilon, right? Because epsilon is the mass dimension of our coupling. And this is what we got. And then what we do, they expand, right? So we got, our final answer was that, the self-energy. We made a couple of replacements. And then we took the epsilon goes to 0 limit. Okay, so this is the same thing as taking the limit to d equals 6, okay? And so that means we can expand a whole bunch of stuff. We can expand the gamma function. We can expand anything that's to the power of epsilon. Right? And we use some tricks like this where we rewrite the Euler constant in terms of a natural log of an exponent. What else do we do? And then we plugged in omega. And this first piece, which contains the pole, you can see the pole as epsilon goes to 0, that part blows up. We can do that by hand because omega is not that complicated. So we could evaluate the integral, and this piece is finite. Okay, so this piece is okay. We're going to do that numerically later on. But we can put things in a nicer form by redefining our mu. That doesn't do it, mu, twiddle was already unphysical, didn't correspond to anything. So if we shift some other parameters into it, who gives a crap, right? And that allows me to write in this nice, simple form, right? This is just our integral part, or just the loop part. And now what we do is we apply our boundary conditions that we're enforcing these boundary conditions on the self-energy, which contains the counter terms as well, right? And this is a particular scheme, okay? So when we talk more in depth about renormalization, we're going to see that this isn't set in stone. You can use other renormalization schemes, okay? And this one is, in particular, is called the on-shell scheme because you're enforcing the self-energy to vanish at k squared equals m squared, okay? And we'll see how the schemes differ. At the end of the day, the physics should be the same, okay? But sometimes there's small differences out to higher orders. All right, so we do some other mathematical tricks, blah, blah, blah. We get down to something like this, right? And here I have my counter terms, A and B, and I want to choose them to cancel off these poles, but I'm also going to choose them to cancel off this dependence on physical scale. Right? So I have that freedom. I also have the freedom to let them have some constant parts as well. And so that's what I did. So I let A and B equal that stuff, right? And that stuff exactly cancels off the other stuff that was in front of it, right? So I'm defining A to cancel off this stuff. And with some constant part kappas, so A and B both have kappa, and those guys are just constants, right? And so we get down finally to self-energy that looks like this. And that's at that point we can apply our boundary conditions to determine what Ka and Kb are. And if you do it, you can actually do this analytically, and that's what the answer looks like. Okay? So I didn't write this down last time, but I told you that it was in the slide, okay? And that's it, okay? At that point, you've got the counter terms determined. You know what the self-energy is. We'll see later on you can use the self-energy to predict how the masses will run with the scale, okay? Because we're going to see that constants aren't constant in quantum field theory, okay? All right, so what we have so far, this is our Lagrangian, right? We already determined y, the counter term y. We did that a couple weeks ago. We just determined z phi and zm because those were A and B. Now the last one we have left is the zg counter term, which is a counter term for the coupling. Okay, so that means we're going to have to compute the 3-point function. Okay, and so I'm going to write the 3-point vertex function like this. It's in bold, meaning that it includes all orders, like what we did before. Right? Remember for the pi, for the self-energy. And what we're going to do is compute this to a fixed order, though. We're going to consider all 1pi diagrams, meaning one part. You guys remember what one particle irreducible means?
Yeah.
It means could I have. So if I compute things to first order. So here's my tree level diagram. Right? Now I'm going to get my loop diagrams by doing what they call dressing the Born. So dressing, right, you just start putting in loops wherever you can. Okay, so I could put in a loop here, and I could do the same thing on this leg, and then I could do the same thing on this leg, and then finally I have this piece. Right? Those are all the same order in the coupling constant. Everybody agree with me?
Mm-hmm.
Yes? Yeah? Are these diagrams 1pi? Are they one particle irreducible? No, right? Because if I can cut this guy right there, and then I get two separate diagrams, right? And I can't get from one point to another, okay? This guy, so all of these guys are not 1pi. They're not one particle irreducible. And we said that we're only going to consider those diagrams, right? When we consider computing these corrections to not only self-energy, but the vertex, okay? And this guy is one particle irreducible because I can cut any line and the diagram stays together, okay? It'll flop open, but you can still get from one point to another, okay? So that's all we mean by 1pi, right? So I'm going to choose my vertex to look like this, my tree level, and I'm going to take all momentum incoming. Okay, it seems a little weird, but you'll see it done a lot because it's just more convenient to have just plus signs coming in instead of some pluses and some minuses. Okay, but we're going to enforce the constraint that the sum of those three give you 0, just from conservation of momentum. Okay, but like I said, you're always free to choose what you want. Okay, so to next to leading order, this is what the vertex looks like. Okay, so we start at order G. This is order G cubed, and then we would move on to order G fifth. Okay, that'll be the final. That'll be the final exam, computing this up to order G fifth. Right. So this is what we want to compute. This guy we know. This is the guy that contains the counter term. Okay, this is what we want to try to determine. So we're going to have to compute this guy. Okay. And so let me apply my Feynman rules. I get 3 factors of vertices, right, and I get 3 propagators. Right. So I'm going to strip those out and just call this thing what's left this interval I3. Okay. And then order Q. Okay. So I assign my momentum. I can do it any way I want, but I always like to assign my unknown momentum so that the first momentum it hits is K1, right? Just a personal choice. So you hit K1, so this is L plus K1. Hit K2, this is L K1 plus K2, okay? Or you could write this as L minus K3, right? Because you have that constraint that K1 plus K2 plus K3 is 0, okay? All right. So what does this integral look like? It's going to get nasty. There it goes. Okay. So it's 3 factors of the Feynman propagator. All right. So it's scalar field. So it's all right. So there's nothing in the numerator. We're going to see when we get to fermions that you get stuff in the numerator as well. And it makes life a living hell. Okay. So I've got my 3 propagator factors right there. Right. And what we want to do is the first step is always combine the denominators using the Feynman trick, right? So we're going to have, in this case, we're combining 3. So there's some factor of 2 here. But what you'll see is most of the time if I'm doing this, in the real world, I won't even write down this 2. Because when I go and do the loop integral, when I do the loop integral, there's a factor of 1/2 that's always going to cancel that. Okay, but just using the formula that's in the book or whatever. Okay, so I'm introducing 3 Feynman parameters to split the 3 denominators, and then I use this delta function to always make sure that they sum up to be 1. Okay, and then my d cubed is something that looks like this. It's a mess. Okay, so once I square out everything, I get something that looks like this. And then if I group stuff together and I use the fact that x1 plus x2 plus x3 is 1, that means I get L squared here, right? And probably the same thing for the mass squared right here, okay? But everything else has factors of the Feynman parameters, either x1, x2, or x3, okay? And so this is the way you want to group it, L squared, order L to the 0, right? And so the name of the game now is we want to get this into a spherically symmetric form. Okay, so we want to complete the square, right? We want to get rid of this cross term. Okay, and so the way we do that is we define some new momentum such that when we square this guy, we're going to get this thing. Okay, we'll get some other stuff with it. Okay, so what I get is if I square everything, I'm going to get something that looks like this. So I'm replacing L squared plus the cross term with Q squared and then some other constant stuff. Okay? And then when I combine that with D, with the rest of D, right, the other constant stuff, I get something that looks like this. Okay? And this is fine. Right now, you could go ahead and say, okay, I got Q squared plus, something, capital omega is what we usually call it, right? But there's a lot of little tricks you can use to make this thing a little more manageable, right? So you can use the fact that you see right here, I have K1 plus K2, and I know I can replace that with minus K3. And then use other tricks to rewrite dot products like this in terms of total squares, right? And if I use my identities, I get something that looks like that. So this term, where is it? Minus 2K1, K1 plus K. So it's this guy. Right? So all that stuff I can replace with these K squareds. All right, I get down to something like this, and then I combine some stuff, and I start noticing that I get 1 minus x2 minus x3, but that's just x1, right? And then same thing here. And so I can get it down to something that looks like this, okay? And these, few lines of algebra are worth it when you go to plug this into a computer, right? It might save you some time, either coding or, in runtime, because the computer's going to have to be able to manage this a lot easier than it manages, what you had before. Okay, so that's what I was going to say. That these are just tricks that you typically use to see if you can whittle it down to something more manageable. All right. Okay. So now we've got the d written in terms of q squared plus some stuff. Okay. And now we can go off, we can plug it into our integral, right? And here I'm introducing some notation that comes from Srednicki. It's just this stuff. It's the integrals over the Feynman parameters times this delta function, and I think it includes this factor of 2 as well, okay? But he just groups all that stuff into this df integral, okay? Right, and so I can plug that back in, and so I get the total vertex, the vertex up to next to leading order. Once I divide out the g, right, goes like this: the zg, and then the g squared term, and then here's our interval that we want to do. Okay. All right. So what we want to do is try to evaluate this guy, but we already noticed that this guy goes like q to the 6 down here, and if we work in 6 dimensions, we're going to have logarithmic divergences. Okay. So that's telling us we need to use our dim reg trick. All right, so we'll go to d less than 6 dimensions and compute it for some general dimension d. All right, the good news is that we've done all the hard work. Okay, we did all the hard work doing when we did that, the integral for the self-energy, and usually the books, quantum field theory books reward you by, having done that, they give you the general formula. Okay, so there's a general formula for some integral of 1 over q squared plus omega to the n power. Okay, so you can go look in the back of Peskin. I mean, that part of Peskin in my book is just completely obliterated because I've flipped it so many times. But it's and I don't remember where it's at in Srednicki, but it's in there. Okay. So the good thing is you can use that master formula, and you can go ahead and write down what the answer is for the loop integral. Okay. And it looks something like this when you whittle it down, right? And you can plug that in, and again, you're going to see omega being integrated over x1, x2, x3, and remember how complicated omega is, right? So so that's going to be a tough integral, and you'll want to go numerically there, okay? But again, we want to keep G dimensionless, okay? So we can't forget about shifting our coupling, right, to G times mu, or mu twiddle, right, to the epsilon power, because we're working in D dimensions, right? And so we end up with something like this, which I can replace. I use that, what do I call it, the reduced constant or something, alpha. Okay, and so we get down to something that looks like that, and that looks awesome, right? It looks beautiful. It's just 2 terms. I mean, how hard can it be, right? There's something else I was going to say. Oh, a lot of times, if you're doing these loops, you don't wait until this very end part to put in this mu. You go ahead and put it in the beginning. I don't know why I do it like this, or why Srednicki does it like this, but it's always good to do it in the beginning, because once you get into calculating these things, there's so many moving parts that there's a chance you're going to forget about it. Okay. All right, so we can take the epsilon goes to 0 limit, or the d goes to 6 limit, right? And expand everything like we did last time. This time, the actual integral for the pole is really easy. It's just 1. And the other stuff is, well, we don't want to worry about that. But we can use that trick again where we rewrite the logs, mu squared over omega. We can separate out the mu squared from the omega. by using, just properties of logs. And that gives us something that looks like our leading term. I think that should be ZG, but anyways. Plus the stuff that we're going to cancel, right? And then, I see what I did. I replaced ZG with 1 plus C, like I did in the self-energy case. We're going to use this C to actually cancel this stuff off. Anyways, I get the pole plus the log of the unphysical scale, right? That's what I want to cancel off. Okay, and then the finite piece, right? And that would be a real contribution to this vertex. Okay, and I want to cancel off the pole and unphysical part, so I can choose my C to do exactly that. In general, can have some constant piece, right? That I call KC. Right. So in the end, our vertex looks something like this. There's the leading part, the next to leading order part, which includes this monster of an integral plus this numerical part. Okay. So far I haven't done anything as far as applying boundary conditions, right? To determine that Kc or kappa C, we need a boundary condition, right? And we talked about this in the beginning. The problem with that is that we don't have enough conditions, right? We only had the conditions on we had the condition on the VEV, right? We wanted the VEV to be 0, and we wanted the single particle states to have the correct normalization. But we had 4 parameters that we had to determine, right? And so what we said was, well, we'll have to rely on experimentalists and hope that they can do their job right? So they can tell us what the real mass of our particle is and what the real coupling is, right? So what we have to do is we rely on experimentalists to give us what the coupling is, okay? And so we I think I do it next slide. We enforce the condition that this function, when I set all the momentum to 0, has to be equal to G, the coupling that they would measure. Okay, this is the condition that we choose, and at that point you find that kappa C is just 0. Okay, and like I said, equation 9, the finite parts of this cannot be done analytically. So this part right here, the DF3, so you got to go numerical on that, okay? Okay, and that's it for the 3-point function. Pretty simple, right?
Sure.
No, but there's, in these loop diagrams, that's why I kind of, when I was doing it, I kind of liked it because there was like a recipe, a formula that you could follow, right? No matter how complicated the diagram was, you knew the steps, right? You use the Feynman rules to write down the amplitude. If it's a loop integral, you can use the Feynman trick to combine the denominators. Loop integral you can always do because we have that master formula, right? And at that point, it's just a matter of whittling it down until you get down to some part that you can't compute by hand. And so you plug that into a computer, okay? But there is a recipe that we're following here, okay? Right. Okay, so now that does it for the 3-point function. What I want to do next is consider n-point functions, so n greater than 3. It turns out that in this particular theory, for n greater than 3, there aren't any tree level diagrams, right? Because there's no 4-point vertex, right? So what we want to consider is a 4-point function. So this guy. All right, so just now we were computing this guy. Now I want to consider this guy, okay? So there's no, what do I want to say? there's no vertex that gives us a contribution like this. Obviously, there is Feynman diagrams because we saw those in the scattering theory, right? Those guys, remember? But what we're talking about are, fundamental. What's the word I'm looking for? I'll think of it in a minute. But just there aren't any vertices that give us a contribution to the 4-point function. You understand what I'm saying?
Yeah,
Okay,
I
I
do.
know it's kind of messed up. But. Okay, so there's no vertices in our theory, so that means the only contributions.
I think I had one. That was one of the problems with early attempts to do a weak theory. Yeah, yeah. They first tried it with just two coming in, two coming out without the mediator.
Yeah. Yeah. We'll talk about that. That's a non-normalizable theory.
Yeah.
But they used it effectively and they predicted the mass of the W, which is pretty incredible. Anyway, so what we want to do is we want to compute this thing, and there's no tree level vertex, so that means that the only contribution we're going to have is going to be things like this, what we call a box diagram. Okay. All right. So if I wanted to compute this, this contribution to the n greater than 3. It's going to come in at a loop order, right? And so let's see what it looks like. Come on. Okay, so it's going to look like this. There's actually 3 diagrams, okay, depending on how you configure the incoming momenta. Right. The nice thing is, did I say it on this slide or not? Right. Yeah. The nice thing is that for these n greater than 3 vertices, if you take a look at the loop integrals, you see that it's going to go like q squared to the n power, and this guy always goes like q to the d, right? And d is 6, right? So if n is greater than 3, these guys will they'll go to 0, right? As you take q to infinity, right? So they're convergent. Okay, so you don't have any divergences in these vertices with n greater than 3 in this 6-dimensional theory. Okay, so that means we don't have to worry about all those tricks as far as we're normalizing stuff. Everything's finite, so we can just compute this guy using algebra and computers, right? So there's 3 different. So this is a good lesson. So you have 3 different diagrams, right? But they have the same topological form, right? They all look the same. And actually, you can get one from the other by just exchanging momenta. Like I can get diagram 2 from diagram 1 if I just switch the labels, K2 and K3, and so forth. So really, it looks like you have to compute 3 of these guys, but really, you only have to compute 1, right? And then whatever the answer is, you just replace, say, K2 with K3, and K3 with K2. Okay, so we only have to really compute 1 diagram, and that's good because these things can be hard sometimes, and you can see why. So here's the diagram, right? And so this is the way we chose the momentum, and so what we get is, so we have our 4-point vertex. There's no tree level piece now, so there's no 1 sitting out here, right? So it's all loop level. We have 4 vertices, 4 propagators. Here's the 4 propagator terms in the denominator. And we want to combine those using the Feynman trick. Okay, so this is going to be, we'll have to introduce 4 Feynman parameters. Okay, and that's going to give us something that's q bar squared, and this stuff to the 4th. And this is what omega looks like. I'm not going to go through the calculation, but it's lengthy, to say the least. Okay? And remember, you're integrating over these guys. Okay? So it's, in this case, it was really, when you first square this thing out, when you're completing the square, it's a mess. I mean, it takes up a few lines, right? And so it takes some work to get it down to this form, but it's worth it. Okay? But you see the same kind of same kind of form that we saw in the 3-point vertex. Right? So again, a loop integral, you compute, right? You compute that guy using the master formula, right? And you see that even I'm computing it in d less than 6 dimensions, just to be safe, but you can see that when I take epsilon to 0, this thing's going to be finite. Okay, there's no poles popping up because you have all these gammas that are going to be finite. Okay, and then omega is just going to give you some logs. All right, so there's no UV divergences, so we just take epsilon and just set it to 0, right? And in the end, we just have the integral of this guy, of all the finite parameters over one of these, right? And then I just do my replacement. So here's the second diagram and the third diagram. Okay, so I've switched. Wherever I have 2, I replace it with 3 and vice versa. And here I do another switch. Okay. This factor is 6. Anybody know where that comes from? Symmetry factor, right? Because it's a vertex. I mean, it's a loop diagram. Did I have it? I didn't have it there, so I slipped it in at the end. Okay. Yeah. All right. And so, like I said, at that point, you go plug it into a computer. Okay. That's just as far as you can get it. I think that's it. Yeah, that's it. So let's take a 2-minute break now while I switch slides over, and then we'll start anew. Okay.